The interstellar object known as 3I/Atlas has once again surprised astronomers, as newly released observations from late 2025 reveal behavior that challenges long-standing expectations about small bodies entering the inner solar system. As 3I/Atlas approached its perihelion on October 29, 2025, a period when it passed closest to the Sun, it exhibited an unusually rapid increase in brightness and an unexpected shift in color, appearing distinctly bluer than the Sun itself. These findings deepen the mystery surrounding this object, which was already notable as only the third known interstellar visitor detected passing through our solar system. The observations are particularly remarkable because at the time they were collected, 3I/Atlas was hidden from ground-based telescopes due to its alignment behind the Sun, a configuration known as solar conjunction. This geometry typically renders objects unobservable from Earth, yet in this case it placed 3I/Atlas squarely within the fields of view of several space-based solar observatories, allowing astronomers to continue tracking it during a critical phase of its journey. The solar conjunction occurred on October 21, 2025, when 3I/Atlas passed almost directly behind the Sun from Earth's perspective. While this alignment is usually unfavorable for observation, it turned out to be advantageous in an unexpected way. Spacecraft designed to monitor the Sun and its immediate surroundings routinely block out the bright solar disk using coronagraphs, enabling them to study faint structures in the solar corona and heliosphere. These same instruments, optimized to detect dim objects close to the Sun, were able to capture images of 3I/Atlas as it plunged deeper into the Sun's gravitational and radiative environment. As a result, astronomers obtained a continuous record of its behavior during the final stages of its approach to perihelion, a region that is otherwise extremely difficult to study for fast-moving, faint objects. The observations were carried out using a diverse set of spacecraft and instruments, each offering a unique vantage point. The Solar Terrestrial Relations Observatory, or STEREO, consists of two nearly identical spacecraft launched in 2006 to study the Sun from different angles. Although Stereo B ceased operations in 2014, Stereo A remains active and orbits the Sun slightly faster than Earth, gradually drifting ahead of our planet. This positioning allowed Stereo A to observe 3I/Atlas from a perspective unavailable to Earth-based telescopes. Data were collected using two cameras from the SECI instrument suite. HI-1, a heliospheric imager designed to track solar wind structures, and COR-2, a coronagraph that images the solar corona. Together, these instruments provided valuable measurements of the object's brightness and spatial extent as it approached the Sun. Additional observations came from the Solar and Heliospheric Observatory, or SOHO, a joint ESA-NASA mission launched in 1995 that orbits around the Sun, Earth L1 Lagrange point. From this stable location, SOHO has maintained a continuous view of the Sun for decades. Its LOSCO coronagraphs, particularly LOSCO C3, were able to detect 3I/Atlas against the background of the solar corona, extending the time coverage of the observations. Complementing these datasets were measurements from JWST, a modern weather satellite launched in 2024 and placed in geostationary orbit around Earth. JWST carries the CCUR-1 coronagraph, a compact but powerful instrument designed primarily for monitoring coronal mass ejections. Despite its primary role in space weather forecasting, CCUR-1 proved capable of resolving details of 3I/Atlas that were crucial for understanding its physical properties. The combined data from these spacecraft cover the months of September and October 2025 and paint a striking picture of 3I/Atlas's evolution as it neared perihelion. One of the most dramatic findings is the rate at which the object brightened. The brightness was found to scale approximately as the inverse of the distance to the Sun raised to the power of 7.5, with an uncertainty of about plus or minus 1. This steep dependence is far more extreme than what is typically observed for comets originating in the Oort cloud at similar solar distances. In most comets, increased brightness near the Sun is driven by the sublimation of ices and the release of dust, processes that generally follow much gentler scaling laws. The rapid brightening of 3I/Atlas suggests that additional or unusually efficient mechanisms may be at work. Equally intriguing is the spatial extent of the material surrounding 3I/Atlas. Observations from the CCUR. One coronagraph resolved the diffuse glow extending out to roughly 300,000 kilometers from the central body. This scale is comparable to the plume of carbon dioxide previously detected by the SPHEREX Space Observatory during observations in early August 2025. At that time, SPHEREX traced CO2 emission around 3I/Atlas over several days, revealing that the object was actively releasing gas well before its closest approach to the Sun. The similarity in scale between the earlier CO2 plume and the later CCUR, one glow suggests a continuity in the object's activity, but also raises questions about the composition and physical processes driving this extended mission. Perhaps the most puzzling result is the color of 3I/Atlas, as measured by LOSCO and CCUR. 1. Photometric analysis indicates that the object appeared distinctly bluer than the Sun during this period, a finding that directly contradicts expectations based on conventional cometary physics. Dust particles typically scatter sunlight more efficiently at longer wavelengths, giving comets a reddish appearance relative to the Sun. Moreover, the surface temperature of a small body at perihelion, while heated by intense solar radiation, should still be far lower than the Sun's photospheric temperature of about 5,800 Kelvin. Both factors would normally result in an object that appears redder, not bluer, than the Sun. The observed blue color, therefore, implies that a significant fraction of the visible light is not simply reflected sunlight, but instead originates from emission processes. Emission in the visible range could arise from several sources, such as excited atomic or molecular species fluorescing under solar radiation, or energetic processes producing ionized gases that emit at shorter wavelengths. However, the strength of the blue color observed in 3I/Atlas is difficult to reconcile with known cometary emissions alone, especially given the object's interstellar origin and presumed unfamiliar composition. Earlier observations of 3I/Atlas, made when it was farther from the Sun, showed it to be red, consistent with a dust-dominated reflection spectrum. The transition from red to blue as it approached perihelion suggests a fundamental change in the dominant source of its brightness, adding yet another layer of complexity to its behavior. Following its perihelion passage on October 29, 2025, 3I/Atlas is expected to re-emerge from the Sun's glare and become observable from Earth during twilight. As it continues along its hyperbolic trajectory, it will reach its closest approach to Earth on December 19, 2025. This upcoming window presents a rare opportunity for detailed study using both ground-based telescopes and powerful space observatories, such as the Hubble Space Telescope and the James Webb Space Telescope. Observations planned for December aim to characterize the object's composition, structure, and activity with unprecedented sensitivity. Based on the trends observed during perihelion, astronomers anticipate that 3I/Atlas may emerge brighter than before, making these observations particularly valuable. The authors of a new study emphasize that the cause of 3I/Atlas's rapid brightening remains unclear. The rate at which its brightness increased far exceeds that of most known comets, even those making their first passage through the inner solar system. This discrepancy suggests that either 3I/Atlas possesses an unusual composition that responds differently to solar heating, or that